So let's look at this one. We are looking at number B3 now, and it's saying consider a reaction with rate low. So here is our rate low. We have rate being equal to K, which is just a constant, then concentration of A squared. By what factor will reaction rate change if concentration is tripled? So I know that the rate is proportional to concentration of A squared. So now I'm tripling A, so I'm going to say when A is tripled, concentration of A is tripled. So I'm going to say concentration of A times 3 squared is equal to the change in rate. I would say change in rates. 3 squared would be 9 is equal to the change in rate. So the factor would be 9. Okay, I would just say 9. Okay, because I'm squaring everything. So I triple it. So I'm multiplying by 3. And this will be 9. Now let's go to part B now. Part B says the reaction A to B has a constant of this, the initial blah blah. When would concentration of A reach this? When is a point, is time. Is asking about time. When would? And the moment I'm asked about the time that the concentration reaches a certain value, they are asking about integrated rate laws. They are the ones that tell me when the concentration would be a certain value. So remember my integrated rate laws, I have 3 of them. Remember, for zero order, we say that the concentration is just going to be the concentration of whoever it is, right, at some function t minus the initial concentration is equal to negative kt. And remember, for first order, we say ln, right? We say ln, the concentration of A at some function t minus ln, the concentration of A initial, is equal to negative kt again. And then for second order now, this good guy, for second order, we say 1 over the concentration of A, some function t minus 1 over the concentration of A, the initial one, is equal to positive kt. It's the only one that gives us positive kt, right? Don't forget that. So let's see. What order is this reaction? I'm going to look at the rate constant, So my rate constant is minutes to the minus 1, which if I only look at the minus 1, just if I put it in modulus, it's going to be 1. So this is a first order. This is a first order reaction. It's a first order reaction. So what does it mean? That means that I'm using this one. I'm going to use this one. So I'm going to say ln concentration of A, some function t, minus ln, the initial concentration of A, is equal to negative kt, which is ln. What is the final concentration? When would it reach the value, this value? Okay, so 0.025. Remember, it's moles per liter. And then minus ln of 0.5 is equal to negative, what's my k? When would I reach? So negative, what's my k? 1.2. So it'll be 1.2 per minute, right? Minute to the minus 1. In here, what was it? Moles per liter. Okay, so you could have it. Let's try to get the thing. Times time t. So what I'm going to do is to get the time t, because it's negative kt, I'll take the negative k. So I have ln of, okay, let me just keep them out, subtracting 0.025 minus ln of 0.5 all over negative 1.2 per minute. This should be equal to t. What am I going to get as my time? I'm going to get, let's put in the calculator together and see what value we get. Okay, the solution would be 2.496. And we know that it would be minutes. So that's the time, because we had this in minutes. So this would be about 2.5 minutes. Okay, so 2.5 minutes is equal to time. So it takes about 2.5 minutes. Then we go to part C. So you should just remember, whenever you are looking for the time it takes to reach a certain concentration, we're going to use integrated rate laws. Okay, I'm going to pause the video here. We'll do part C in the next one.